how to choose L and C. This ripple current is more important because this is used almost everywhere, all the calculations. So, better you remember this equation rather than remembering this voltage, in case you cannot remember both. So, this is your ripple current, this is your ripple voltage. So, for the same LC product and same switching frequency, same VDD, which means same output. So, your duty cycle same, everything remains same. Okay. I can choose different L and C. I can. It is a product which matters. As long as the product is constant, L and C. So, assume that rest of the things remain same. For the same ripple current, let us say I want to design for the peak to peak ripple current of 10 millivolt. So, this product I can choose, let us say L equal to 1 microhenry and C equal to 10 microfarad, or I can exactly do the opposite. I can have a L 10 microhenry and C 1 microfarad. It will give me the same ripple according to this formula. So, how do we choose in that case? Which one should be large, C or L? L should be large. Why? No, but if you use a smaller cap, then what will happen to your transient response? Okay. So, now case 1. For the same delta V out. Okay. So, delta L is small, ripple remains same. What does it mean delta L is small? Which means? No, that is fine, but what about the slope? Reduces, huh? That is what causes your ripple reduction. You are not changing the time period, but you have changed your current rise and fall, and that is why it will not go to the same value and your ripple current will reduce. And what do you prefer in case of transient? You want the current to rise very quickly. So, you have a double effect here actually. Double effect in the sense your inductor is not reaching to the peak current which is required by the load quickly, and during that same time capacitor has to supply more charge to the output. So, basically your load will draw more charge from the cap and you have reduced the capacitor. So, it has a double effect. So, transient response will be very bad in this case. So, this implies transient response will be poor. Okay. So, if you want to look at it, so if this is your load current I load, and this is your inductor. So, inductor current will rise something like this. Let us say you have given full 100% duty cycle during transient. Okay. So, usually what happens, this goes like this and then it will settle. Okay. So, what happened to this region? Whatever the difference of your load and this. So, this much charge is drawn from the cap, which means, and this region is more if that is slowed down. If it is a faster, then it will reach quickly and that region will shrink. Case 2. Case 2 will be exactly opposite. L is small and C is large. So, one more benefit you get here, inductor delta L is small, which means RMS losses are okay, because your peak to peak ripple current is less. So, RMS current will be less. So, your conduction losses or other losses which are associated with only ripple current, they will be reduced. Delta L is large, higher RMS losses, then inductor current slope increases, which means first and capacitor is also large. So, this will lead to better transient response. So, this is the case with large L, small L. Okay. So, that triangle, actually area of that triangle is reduced and capacitor is also increased. So, you get a square factor of reduction in the undershoot or improvement in the transient response. But in this case, what is the drawback here? RMS losses. Another thing is requires requires inductor with higher okay. So sometimes what happens, I mean most of the time we try to reduce the inductor, but make sure it does not crosses your the peak current, it does not crosses your saturation current of the inductor, otherwise inductor will saturate and it will break. Okay. So if you are more concerned about the ripple current or you are using an inductor which has a very low I sat, then you have to go with case 1. But if you have an inductor which has a very high I sat current, then you try to minimize L and increase C in that case, because that will help you in transient response. Okay. And most of the time what happens, if you look at the inductor trend, the smaller the value of the inductor is, the less windings are. So, your resistance will reduce, okay, and the area of that core is also small. If that inductor is smaller, then core area is smaller. So, your magnetic losses will also be less. Okay. So, saturation current will be higher. So, you pick I mean same series of the inductor. So, from the same series means they are manufactured using the same material, same core, everything. So, use a 1 microfarad, you look at a 0.47 or half microfarad, microhenry, and 0.2 or 0.1. As you reduce the values reduce, you will see your I sat will start increasing and DCR will also start reducing. Okay. We will look at the data sheet probably in the next class. For these inductors, what are the parameters which are given in the data sheet, and how you read actually inductor, how you read, how I sat is defined, how your DC current for inductor is defined. So, all those mostly based on temperature and peak current actually. Okay. So, that is how when you start designing, you choose your inductor. So, you look at what value you require of the inductor and then see if there is a and you can easily calculate the peak current. You know V in V out, what will be the duty cycle. Okay. And if your V in is fixed and V out is changing, then the worst case will be 0.5 duty cycle. At 0.5 you calculate the peak current and see if the inductor you are selecting, it can afford that much peak current, and usually you keep some margin also, because you do not want to just hit the I sat value. Okay. So, usually saturation of inductor is defined when the value is falls 30% below your typical value. So, if you are using 1 microhenry and the current at which it goes 0.7 microhenry, that defines the saturation current. That is soft saturation, but there is something called hard saturation also, where the inductor will fall very quickly. So, in that case, that is defined almost like 0.9 or so. Okay. So, it depends on types of inductor. If you are using magnetic core, then it will have mostly like hard saturation. If you are using iron core or air core kind of inductor, then it may have a soft saturation. Okay. So, we will look at all those saturation curve and data sheet next class. So, any question?
Sir, what about inductors which are implemented using other element?
Which other element? What do you mean by other element?
I think it's called Capacitor or something. Using capacitor.
No, they cannot afford to carry this current. You need a real inductor. Those are like artificial inductors. Where the current has to flow, this 1 amp current, your load current, who will carry that current? Your op amp cannot carry that current. And ultimately all those currents have to come from the supply. Even let us say you designed op amp which can carry 1 amp current, it has to come from supply, it will kill your efficiency. Okay. If your op amp is let us say 5 volt and your output is, you have designed, so one end is at 5 volt, other end is at 1 volt or so. So, you are losing it's 1 amp current is flowing and you are losing 4 volts. So, it is like you have designed a very bad LDO which is dropping 4 volts. So, 4 watt 5 watt will be lost in your gyrator itself. So, it will kill your efficiency. We never use for power application those. They are only meant for filter, because there is no as such DC current there. All it's you have to just filter out the signal, that is it. But for any DC load current, this power application, you never use those gyrator kind of inductor. You always use real inductor. A real inductor also very high quality inductors. You cannot even use the on chip inductors or on board inductors for this, which has a very bad Q. So, you need a very high Q inductor for these kind of applications, otherwise your efficiency will be very bad. Okay.